Not sure what happened, but I apologize for that. Let me share my screen. Man. All right. Today we're going to do a couple of things. We're going to kind of revisit the hybridization discussion, and then we're going to talk about some different ways to write structures, and then we're going to talk about formal charge. And that's going to also lead us into a discussion about functional groups and things like that, which is in the first module 1A. Right. But for now, we're still in the first module, and we're just going to talk about, let's go back. I had a couple of questions I wanted to touch real quick. And then let me actually, I'm going to take this and copy it. Blank page. All right. So with this question right here, we're going to kind of push this hybridization, the idea of hybridization a little bit further. And it says predict the hybridization and geometry, right, around each indicated atom. And if you remember, sp3 is tetrahedral. Today's the 31st. Right, sp2 is trigonal. And then sp is linear. Right? sp3 is trigonal. I'm sorry, tetrahedral. sp2 trigonal. sp linear. Now let's look at, because this will give us a chance to touch another topic too. So I want to look at A, C, E, and F. Right. So I know there's a question in your mind right now. If we're only doing these, what about the other ones when we turn it in? These are the problems that we're doing to discuss this topic. All right. So G, B, and D, you're not responsible for unless I assign them. Right. But I'm not going to assign them in this instance. All right. So let's take A. A is CH3. So I'm going to write this out so you can see it. CH2. Now, if you notice, there's a negative charge here on carbon. So we have to account for that, right? So the way that you account for that, and I'm going to show you a couple of things in addition to talking about the hybridization state. What that negative charge indicates is that there is a lone pair on carbon, right? This is when carbon is negative, it's called a carbanion. Anytime you see a carbon with a negative charge, that means it has a lone pair on it somewhere. Right? You have to account for that, right? The way you calculate that charge, this is another learning objective. You just take the valence electrons and subtract out from that what I like to call actual. And you get the formal charge, right? So let me explain what I mean by actual. Well, first, what's valence? What do we know about valence? How do we determine that number? Anybody? How do we determine the number of valence electrons for any atom?
Its location on the periodic table.
There it is on the periodic table. The atomic number is going to tell me how many electrons it has. So for carbon, what's the atomic number for carbon? Not the mass, but the atomic number. What group is it in? If you look at the periodic table, you start at boron. Boron is group 3. The next group is group 4. Right? So that means that it's got 4 valence electrons. Are y'all following? Everybody okay with that?
Yes, sir.
So carbon has 4 valence electrons. So the actual is going to, well, the valence is going to be 4. And then if we look at the molecule itself, that's how we get the actual. So we're going to look at the bonds and lone pairs, right? That's how we get actual. So we look at the bonds and the lone pairs. So the actual is going to be half of each bond and any lone pair. So it's going to be a total, right? So let's look at it. So we got 2 here and then 1 from each bond. So that'll be 1, 2, and then 3 for a total of 5. So 4 minus 5 is -1. So that's how we calculate the formal charge for any atom is valence minus actual, right? And we're going to do more, but I just wanted to go ahead and give you that because it was appropriate. I mean, we're right here. So, and why waste energy in your brain worrying about the charge and where it came from, as opposed to just going ahead and putting it out there. All right. So now we got the charge part out of the way. Now we need to answer the question, what's the hybridization state and the geometry? Remember, a lone pair on any atom is going to be located. It's not just sitting there. It's actually going to be located in an orbital. So that orbital is going to have a shape, right? It's going to have a direction. So how many groups are around this carbon, including the lone pair?
4.
4 groups. Excellent. So you got a hydrogen here, 1 here, you got a lone pair, and then this carbon here is also a group. So this carbon has 4 groups. And we know based on our previous conversations and discussions that an atom that has 4 groups around it is sp what?
SP3.
Excellent. I said xp3, sp3. Excellent. All right. If that's the case, what's the geometry? We know, if we know it's sp3, then we know the geometry as well, because the geometry of a sp3 atom is going to coincide with the fact that it's got 4 things around it. So the geometry is tetrahedral. Anybody not see that or not following? This is A, by the way. Any questions about that?
On the worksheet, do we just have to write the answer, or do we also have to show the work?
It would be really beneficial to you to actually be following along and showing the work, because that's going to develop some muscle memory and it's going to help you to understand what's going on. So yes, your worksheet should kind of look like like the notes that we're taking right now. Otherwise, you just could not show up and then just get the notes off Blackboard and write the answers in. And that's not gonna be beneficial at all. All right, let's do C. Go ahead.
Is it okay if we write the answers on the paper but have our work on another sheet and just turn it in as well?
Yeah, you can do that. As long as you scan it all in together, that's fine.
Okay, thanks.
Yeah, because I know there's not a lot of room on the sheet itself. I get that. So if you want to put the notes somewhere else, that's fine too. Yeah. All right, let's do C. C is oxygen. It has a plus charge, so it's oxygen with 3 methyl groups attached to it. Oh. Three. And let me give you another nugget, right? This 3, because we're going to be talking about condensed formulas in a minute. right? This 3 tells me that there are 3 groups here in these in parentheses, right? That subscript tells me how many of those groups are bonded to oxygen, right? If you write it like this, right, it's called condensed. It's called a condensed formula, where I don't write it out like this with the group shown. I just put them in parentheses and put a subscript. All right, so that's the condensed version of that. And oxygen in this case is going to have a lone pair and a positive charge. All right. How do I calculate that positive? How do I know that charge is going to be +1? What can I do to figure that out? It's going to be valence minus actual, right? That's going to give me the formal charge. What's the valence of oxygen? How many valence electrons does it have? If you ever have a question about that, just look at the group number. So boron is group 3, carbon is group 4, nitrogen is group 5, oxygen is group 6. All right, so oxygen has 6 valence electrons. And then how many are actually around it? 1 from each bond. So that's 1, 2, 3, and then a lone pair makes 5. So 6 minus 5. And that's how we know that the charge on an oxygen with 3 groups attached to it, or 3 bonds to carbon, is +1. Questions about that? All right, now let's answer the other question about the hybridization state. How many groups are around this oxygen? A lone pair is a group.
4.
4.
Okay, excellent. So 4 groups. So that means it's what? SP what?
3.
SP3. What's the geometry?
Tetrahedral.
Tetrahedral. Good. All right. Anytime it's SP3 hybridized, the geometry is going to be tetrahedral. All right. Let's look at E.
I have a question.
Come on.
So basically, when we look at equations like this, we always go towards the end, the atom at the end. So last time we did the carbon that was negative, and now we're doing the oxygen.
Well, we're just doing the ones they're giving us up here, right? We could have done
towards the arrow.
Yeah, we could.
Okay.
Because the question asked to predict hybridization and geometry around each indicated atom. So it's just, we're just doing what it's telling us to do. But we could have done any of them, right? Because those CH3s are hybridized as well, right? They're all SP3. And in this case, they're all SP3. But yeah, we're just following what the example. All right, let's do E. There's no charge, so we don't have to worry about that. What is the hybridization state on E, and how do you know? How do we tell? There's a couple of ways we can tell, right? What's one way?
Looking at the triple bond.
Look, a triple bond gives it away, right? Any atom with a triple bond to another atom is going to be in a specific hybridization state, right? In this case, if it has a triple bond, what's the hybridization state?
SP.
SP, excellent. It's SP hybridized, right? The other way is to look at the number of groups. If this is the atom that we're looking at, it's got a CH3 out here. It's got another carbon on that side. So it has 2 groups attached. Groups, bonds, totally different, right? Every carbon, if it's not charged, is going to have 4 bonds to it if it's neutral. So in this case, you can see the 4 bonds to that carbon. It's got a triple bond on one side. That's 3 bonds. And then it's got a bond here to make the 4th bond. All right, questions? Any questions about that one? All right, let's take F. I'll write it down here. It is, we're gonna actually do all the atoms in F. Oh, CH3. All right. Now let's look at we're gonna do the nitrogen first because that's what it asked for, but we're gonna do all the other ones too. What do you think? What's the hybridization state? It's neutral, so we're not worried about the charges. But what is the hybridization state and the geometry of nitrogen?
Is this for nitrogen or oxygen?
Nitrogen.
I think for nitrogen, the hybridization state is sp2.
Good. sp2, you're right. Remember that lone pair. Actually, I'm gonna draw this differently because you'll be able to see the geometry. The lone pair is actually in an orbital, so it's kind of out here. And then the oxygen is here. Right? So you're right, that nitrogen is sp2. Two ways to tell. First way is it has a double bond to it. You can see that double bond. The other way to tell is the number of groups. So this is one, that's a group, and then this carbon over here is a group. So it's got 3 groups around it. That's one way to tell. The other way is to look at the fact that you have a double bond, right? What's the geometry? Remember,
Trigonal.
good, excellent. If it's sp2, the geometry is trigonal. All right, let's do this carbon right here. What do you think?
Is it still sp2?
It's also sp2. Good. And it is also trigonal. Is that right? And if it's drawn out like and with the geometry, you can actually see that triangle and that 120-degree bond angle. You can kind of see it right here. Like that, and then you can see it on the other side too. All right. What about the oxygen down here? What do you think?
sp3.
sp3, excellent. Change my tip back, sorry. This is sp3. How'd you come to that conclusion?
Because it has 4 electron regions, and then because it's still, I guess, like the electron lone pairs still act as like the orbitals.
Good. That's exactly right. You said a really key term, electron regions. So that's what, when we say groups, that's kind of what I mean by that, right? It's those are the places where electrons are present either as lone pairs or overlapping with other electrons and other atoms to make bonds. All right, good. This is good. All right, let's go back to the next example. Yes, we started on this example right here. We said that here, this was sp3, sp3 overlap. I just didn't get a chance to write it on the screen because we were having some issues. And we said that right here, this hydrogen overlapping with this carbon, the hydrogen was S and the carbon was sp3. So we said that this was sp3s overlap. Is that right? So now let's look at B and D. We're going to do B and D. All right, so we're gonna do these two, right? And it's got three different bonds that it's looking at. So let's do the middle, this bond right here first, right? The double bond. What do you think? That double bond has this has a hydrogen coming off of it. It's not shown. We're gonna talk about that in a second. The difference in skeletal forms and Lewis forms. But I wanna finish out this hybridization idea first before we switch topics. All right. Each carbon in that double bond, what's the hybridization? What do you think the hybridization state is?
SP2.
They're both sp2, right? So the double bond, remember the double bond is two bonds though, right? It's a sigma and a pi, right? So for the sigma bond, are y'all following that? Do y'all remember that? We talked about that the other day. Every double bond is a sigma, one sigma and one pi.
Yes.
Okay. So let's say for the sigma bond, what's the overlap? What has the overlap in this instance with that double bond between those two carbons? What's overlapping? What types of orbitals are overlapping? Is it the hybrids or is it the unhybridized orbitals? Because remember, for sp2, you got 3 hybrids and you have 1 unhybridized p orbital. Is that right? So for the sigma bond, which orbitals are overlapping to make that bond? I know that sounds crazy because we haven't talked about, well, we kind of introduced valence theory and orbital overlap, but I haven't gone into great detail, but I am because we're going to talk about polarity and things like that. What do you think though, for the sigma bond?
The SP orbitals.
It will be your hybrids that are overlapping. So for that sigma bond, it's going to be sp2 overlap. And then for the pi bond, what's overlapping?
The p orbitals.
The unhybridized p orbitals. Good. So that's going to be p overlap. You can laugh later if that sounds goofy to you. All right. So the pi bond is the unhybridized p orbitals overlapping. Sigma bond is the hybrid orbitals overlapping. So for that sigma bond, it's going to be the result of sp2 because both carbons are sp2 in that double bond. And then the pi bond is going to be the 2 p orbitals to the 2 unhybridized p orbitals on each carbon atom overlapping. All right, questions about that? Because I just said a lot of words and I don't want anybody to get lost in the sauce. So if you have a question, this is a good time to ask it.
Yes, I have a question. Could you
Hmm.
actually just re-explain, like, okay, so the sigma, like the hybridization overlaps with the sigma bond and the pi
Yes.
bond, like the difference in the two?
Yeah, let me I'll just redraw it. Let me copy this example. I'll just redraw it because I should have done that from the jump. That way we'll have more room and I could have expanded it. That's okay. You live and learn. All right. So remember, if a carbon is sp2 hybridized, I gave a model, right? That it looks something like this, where it has a hybrid. This is the trigonal part here, here, and then here. Is that right? That's my triangle. That's flat. And then the unhybridized p orbitals are here, perpendicular to that. So it's kind of like if this was a straight line, right? The p orbital would be here, and then the other orbitals would be coming out here, 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 like that. right? So it's planar. So the p orbital, I'm gonna go ahead and shade it. The p orbital is above the plane and below the plane. And so in that particular bond, that's overlapping with another sp2 carbon. So that's going to look like this, right? Where you have another sp2 carbon here. Same trigonal geometry. And then it also has the p orbitals here. I'm going to shade that too. All right. So the sigma bond is going to happen right here. Because the two sp2 hybrids are going to overlap and share electrons. And then the pi bond is going to happen right here. That's that p overlap. All right, so your in a double bond, your sigma bond is when the hybrids are overlapping, and then the pi bond is from the unhybridized p's overlapping. If you remember when we talked about hybridization for sp2, it was sp2. You had 3 sp2 hybrids, and then 1 p that wasn't hybridized, and each one of them had 1 electron. All right. So did that answer your question somewhat?
Yes, it did. Thank you.
Okay, good. All right, let's go to the next one right here, right? Because it's asking us now for this bond. What do you think? We know that this carbon is sp2 because we just said that. What is the hybridization state of that carbon right there?
SP3.
sp3, excellent. Great work, that's sp3. So when those two atoms come together to make a sigma bond between them, what's overlapping? It's sp2, sp3 overlap. Yes or no?
Oh, okay. I have a question.
Come on.
So since we had already identified like the carbon that we're on now, that is sp3, since it's bonded to the carbon that's in sp2,
Yes.
then it's an sp2, sp3 overlap.
Yes.
Okay, I get it. Thank you.
I can feel the light bulb that came on just now. That's good. Well, but you're right. That's what that is. All right, let's do the top. We got a hydrogen bonded to a carbon. That carbon, we already showed that a second ago, that it is what? This is sp2. Is that right? We already showed that. What about the hydrogen? We talked about that. It can't hybridize. There's only one orbital, and that's the 1s orbital. So what's the overlap here? Is the sp2 carbon going to overlap with the s orbital of hydrogen to make that sigma bond?
Yes.
Yes. So that's the overlap. Those are the orbitals used to form that bond. The sp2 hybrid from this carbon right here, and the s orbital from hydrogen. Is that making sense? Are we okay?
Yes.
All right. All right, let's do the last one down here. There are a lot of arrows, so we're gonna have to do a lot, right? But let's do the single bonds first. All right. First, let's do the hybridization states of each atom, and then that makes everything else cake. All right. So let's start here. We're just gonna do the carbons, right? Hydrogens can't hybridize. So the carbons right here and the triple bond, what's the hybridization state of those carbons? Anytime you have a triple bond between two atoms, they're going to have a Good. They're going to be in the SP hybridization state. And what about this carbon right here? That's double bonded to nitrogen.
SP2.
SP2. Great. What about the nitrogen? It has a lone pair, by the way, just not shown. It has a double bond to it. I heard it. Did you say SP2?
SP2.
Good.
Yes.
What about the carbon here, the CH3?
SP3.
SP3. And then we know that this is S, right? It's just one S, a 1s orbital. It's not hybridized. All right. So now let's go back. It's asking, let's start here. What's overlapping there? This carbon is bonded to hydrogen. Is that right?
S and SP.
Good. Excellent. So it's S, SP overlap. Great. What about on this end down here? That carbon is SP3. The nitrogen is SP2. So what's happening with that bond right there?
SP2, SP3 overlap.
Good. All right. Now what about here between the carbon and the nitrogen? These two. It was already written out, but it's SP2, SP2 overlap. Is that right?
Yes.
All right. What about here? It's this bond right here that it's asking about.
SP and SP2 overlap.
SP, SP2. Good. Excellent. All right. Now, what about the triple bond? There are 3 bonds in there. There are 2 sigma bonds. I'm sorry, 1 sigma bond and 2 pi bonds. So for the sigma bond in that triple bond, what's overlapping? Remember, sigma bonds come from hybrid overlap. So what's overlapping in that triple bond to make the sigma bond?
SP, SP overlap.
Good. It's SP, SP overlap. And then what about both pi bonds? Doesn't matter. They both gonna be the result of the same thing. So you got 2 pi bonds, and pi bonds always are the result of the overlap of unhybridized p orbitals. Is that right? So for the pi bonds in that triple bond, it's going to be what? PP overlap. Is that right? For both of them. Questions about that? Everybody got quiet. All right, we're good on that example?
Yes.
Okay, great. All right. So now let's
Excuse
go
me.
back. Go ahead. You had
I'm
a
sorry,
question?
before we go on, can we go back to right there, the C and F for 169? I missed the part of it.
Right here?
Thank you.
Mhm.
Okay.
All right. If you ever have a question or you miss something, and this is for everybody, just stop me. I don't like to think of the class as like a dictatorship where I just talk. I want it to be a discussion, and I also want you to feel like you can ask questions at any time, or hey, slow down, moving a little too fast. Please let me know. There's no point in me just running my mouth if you're not getting anything out of it. So anytime you miss something or need something back on the screen, just say something. Yeah, we're done with that example. Let's go to, I want to assign this problem to you. 171. So when you turn this in, this problem, you need to finish it on your own. I'll just give you A. And I'll put on your own. All right. Just so you can get more practice with that. And we've done already 169. So now we're gonna talk somewhat about drawing structures. And I'm going to take this example, put it on a blank sheet so we'll have room to work. Right. Normally, when you see a structure like the ones that we've been working on, those are all what we call skeletal structures. But there are a couple of ways to depict molecules. You can do what we call Lewis structures. Right. In a Lewis structure, you're going to show everything. Right. So you're going to show all your atoms, all your bonds. You can do a condensed structure where you use parentheses to group up identical functional groups. I'll just say identical substituents. Right? Or you can do what's called a skeletal form. This is the easiest to draw, but the hardest to read initially. And the best way I can do, the easiest, simplest way I can define this is that you only show the backbone. No carbons, no hydrogens, right? You don't show them. They're understood to be there. So in the example, so the example is asking us to convert into a skeletal structure, but we're going to actually, for the ones that is possible, we're going to do the Lewis and the skeletal. So let's take, say, like A. Let's take A. A is actually condensed already. Right, this is condensed. The way you can tell it's condensed is by the subscripts. So you got these little subscript numbers here and the parentheses, right? That's telling you that that's grouping up some functional groups. And because they're identical, you put them in parentheses and you use a subscript, right? So what I want to do is draw this out in Lewis form. So we're going to take all the carbons. We're going to draw them out and show the bonds between them. So let's see. And then on this carbon, the subscript 2 means that there are 2 CH3 groups attached to that. All right, so I'm going to draw those out like this. C. And I'm going to write out the hydrogens too. C, like that. Put the hydrogens in. The Lewis form is very cumbersome. Right, and then on the other end, it's the same thing. C, like that. All right, and then let's go back to the backbone. It has, this is CH, so I'm going to write in a H here, like that. And then here, these are CH2s. And then this is also a CH. So this is the Lewis form. Right? If you notice, there are 1, 2, 3, 4, 5, 6 carbons in the longest chain. That's a very important concept for later, right? So if I were to sketch out the longest chain, I can start from either side, but I'm gonna start here like that, right? And if you'll notice, there are 6 carbons in that chain. 1, 2, 3, 4, 5, 6. Right? If I went the other way, that would work too, but it's still gonna be the same number of carbons in the longest chain. So if I change the color of my highlighter, if I went that way, that's still gonna be 6 carbons. 1, 2, 3, 4, 5, 6. So it's the longest chain that we call that's the backbone. Another term for that is the parent chain. So that's the parent chain. All right, give me one more minute. So if you notice on the Lewis form, everything is drawn out. In the skeletal form, it's the exact opposite, right? So I'm going to find, but I need to know what the longest chain is before I can draw the skeletal form. So I'm going to take that. There's 6 carbons. I'm going to draw it like this. All right. And because there are 6 carbons, notice it took me 5 strokes. I'm going to do it again. 1, 2, 3, 4, 5. This is the skeletal form. Every vertex is a carbon, and the end of every line is a carbon. Right, so that's 6 carbons. Now, if you look at the Lewis form, I'm missing 2 carbons. Right, I'm missing this one and this one, so I'm going to put them in like right here. So it's here and here. So now I have a total of 8 carbons, but there's 6 carbons in the longest chain. Right, so this is a CH3. This is a CH3. And this is my skeletal form. I don't show any C's or any H's except where I designated necessary. So I can, because the end of every line is a CH3, unless there's another atom there. We call it a terminus. So every terminus is a CH3. And then every vertex where 2 lines come together, that's a CH2. All right, that's very important because a lot of times when you see the skeletal form, sometimes it's not clear what it is, why am I drawing it that way? But if it's in skeletal form, the end of every line is a CH3, every vertex is a CH2. All right, and then right here, you can see that this carbon right here, you can see 3 bonds to it here, here, and here. So the 4th bond is understood to be hydrogen in that situation. We'll pick up this on Friday. We'll pick this up on Friday. We got to stop now because I'm over time. Any questions about anything before we stop?